March 14, 1945. The air hangs heavy with diesel fumes and the metallic tang of oil beneath a gray English sky. In a repair depot 30 miles south of London, a young American mechanic named Robert Bobby Hendricks kneels beside the exposed engine of an M4 Sherman tank. His hands blackened with grease, his eyes narrowed in concentration. Around him, the cacophony of war echoes softly. The distant rumble of bombers returning from raids over Germany. The sharp clang of hammers against armor plate. The shouted orders of sergeants organizing convoys bound for the continent. But Bobby hears none of it. His entire world has contracted to the small brass device in his palm, no larger than a pocket watch, its surface etched with calibration marks that catch the weak afternoon light. To every officer who has inspected it, to every engineer who has dismissed it, this object is nothing. A curiosity, a waste of precious war materials. To Bobby Hendricks, it is salvation. The Sherman tank, by the spring of 1945, carries a reputation as contradictory as war itself. American soldiers call it the Ronson after the cigarette lighter, because it lights the first time. Every time, a grim joke about how quickly these 30-ton machines erupt into flames when struck by German shells. The British, with their taste for understatement, refer to it as the Tommy Cooker. Crews whisper survival statistics in hushed tones between missions. Average lifespan after first combat engagement, 6 weeks. Average crew survival rate after penetration, less than 50%. Yet the Sherman remains the backbone of Allied armor, rolling off assembly lines in Detroit and Cleveland at a rate of 2,000 per month, flooding across Europe in numbers that German commanders find incomprehensible. It is not the best tank. It is not the strongest tank, but it is the American tank. And therein lies both its weakness and its unexpected strength. The device Bobby turns over in his hands addresses a problem that has haunted the Sherman since its first deployment in North Africa in 1942. The Wright R975 radial engine, a beast borrowed from aircraft design, generates 400 horsepower and consumes fuel with an appetite that matches American industrial confidence. But this engine, this magnificent piece of engineering, suffers from a fatal flaw in the crucible of combat. It overheats. Not occasionally, not under extreme circumstances, consistently, predictably, lethally. When a Sherman crew pushes their vehicle across the broken terrain of France, up the muddy slopes of the Ardennes, through the shattered streets of German towns, the engine temperature climbs, oil thins, gaskets fail. In the worst cases, the engine seizes completely, transforming a mobile fortress into a stationary coffin, waiting for the next 80-diameter shell to find its mark. Army engineers understand this problem. Technical manuals acknowledge it. Maintenance crews work around it. The official solution involves careful monitoring of temperature gauges, regular cool-down periods, and strict operational limits that combat conditions routinely obliterate. Tanks do not fight on schedules. Battles do not pause for engine maintenance. When panzer units counterattack at dawn, Sherman crews cannot request a 15-minute cooling break. They advance or they die, and frequently they do both. Bobby Hendricks did not set out to revolutionize armored warfare. Born in 1923 in Terre Haute, Indiana, he grew up in the shadow of his father's garage, a small operation that serviced farm equipment and the occasional automobile. His education in mechanical systems came not from textbooks but from necessity, from fathers and uncles who could not afford to replace what could be repaired, from a Depression-era childhood that taught improvisation as a fundamental survival skill. When he enlisted in 1943, the Army recognized his aptitude and assigned him to the 23rd Ordnance Battalion, a unit specializing in armored vehicle recovery and repair. By the time his unit arrived in England in preparation for the Normandy invasion, Bobby had already logged thousands of hours inside tank engines, his hands learning the language of metal and combustion that words could never fully capture. The idea came to him not as a flash of inspiration, but as a slow accumulation of observations. Sherman after Sherman arrived at his repair depot with the same constellation of symptoms: warped cylinder heads, cracked engine blocks, seized pistons. The official explanation cited combat stress, poor crew maintenance, inadequate lubrication, but Bobby noticed patterns the official reports missed. Engines failed most frequently after sustained high-speed operations. Failures clustered in units that fought in summer heat or pushed through rapid advances. The technical cause remained consistent: thermal expansion exceeding the engine's design tolerances, creating cascading mechanical failures that no amount of field maintenance could prevent. The Army's solution involved better crew training and more frequent inspections. Bobby's solution involved physics. If the engine ran too hot, reduce the heat. If thermal expansion caused failures, control the expansion. Simple in concept, seemingly impossible in execution. The Sherman's cooling system was already operating at maximum capacity, its radiators and fans designed by engineers who understood thermodynamics far better than a 22-year-old mechanic from Indiana. Yet Bobby persisted, driven by a conviction that bordered on obsession. He spent his off-duty hours sketching designs in a battered notebook, calculating heat transfer coefficients with a slide rule purchased from a departing lieutenant, testing prototypes fashioned from salvaged parts in the darkness of the depot after official work ceased. His device, when it finally took shape in the winter of 1945, looked absurdly simple: a small chamber connected to the engine's oil circulation system, containing a series of baffles and a thermally reactive compound Bobby had synthesized from automotive additives and aircraft coolant. The principle relied on phase change cooling. As the compound heated, it absorbed thermal energy through evaporation, then condensed and recycled through the system. The entire assembly weighed less than 3 pounds. It cost approximately $7 in materials. It required no external power source, and according to every engineer who examined it, it should not work. The objections came immediately and from every direction. Senior mechanics pointed out that oil temperatures in combat conditions could spike by 200 degrees Fahrenheit within minutes. No passive cooling system could handle such extremes. Engineers noted that any device inserted into the oil circulation could reduce pressure and flow, potentially causing lubrication failures worse than overheating. Supply officers dismissed it as a waste of resources, an unauthorized modification that violated Army technical manuals and could void manufacturer warranties, as if warranties mattered to crews fighting through Germany. The most damning criticism came from a visiting colonel who spent 30 seconds examining the device before declaring it a useless gadget and ordering Bobby to focus on approved maintenance procedures. But war creates its own authority structure, one that runs parallel to official hierarchies and often contradicts them. Tank crews, the men who actually fought in Shermans, who felt the interior temperatures climb toward unbearable levels during combat, who had watched friends burn, possessed a different perspective. When Bobby mentioned his device to a crew waiting for their tank to be repaired, they did not ask about engineering principles or Army regulations. They asked a single question: will it keep us alive? Bobby did not know. He thought it might. That was enough. The first installation happened without official authorization on a cold morning in late January. The crew of Betty Lou, a Sherman commanded by Staff Sergeant Mike Torres from San Antonio, volunteered their tank for the experiment. The work took Bobby 6 hours, most of it spent carefully integrating the device without disrupting existing systems. He tested oil pressure at multiple points. He checked flow rates against manufacturer specifications. He ran the engine at idle, then at combat speed, monitoring temperatures with a borrowed pyrometer. The results showed a reduction of 43 degrees Fahrenheit in peak oil temperature, under sustained high RPM. Operation modest, measurable, potentially significant. The true test came 3 days later when Torres's unit received orders to support an infantry advance near the German border. The operation involved a 15-mile approach march, followed by engagement with dug-in Wehrmacht positions. Under normal circumstances, Sherman crews would push their engines hard during the approach, then face critical decisions during combat: maintain operational tempo and risk overheating, or throttle back and sacrifice tactical mobility. Torres reported after the mission that his engine temperature never entered the danger zone. While other Shermans in his platoon paused to cool their engines, Betty Lou maintained full combat effectiveness. No mechanical failures, no forced stops. The crew returned alive, their tank intact, and within 24 hours every other crew in the battalion wanted Bobby's useless gadget installed. Word spread through informal networks that define military life. Tank crews talk to other tank crews. Mechanics share information across units. A device that might improve survival prospects travels faster than any official memo. Within 2 weeks, Bobby had installed his cooling system in 17 Shermans. Within a month, mechanics in other units had examined the design and begun producing their own versions. The Army's official position remained unchanged. The device was unauthorized, unsupported, and untested, but officers who actually led tank units increasingly looked the other way. A lieutenant colonel commanding an armored battalion put it simply in a letter to his division commander. "I don't care if it was invented by a fortune teller using chicken bones. My tanks run cooler and break down less. That's all I need to know." The German soldiers who encountered these modified Shermans noticed nothing different. The tanks looked the same, sounded the same, burned the same when struck by the dreaded 80mm anti-tank guns that remained Germany's most effective tank killers. But the crews inside experienced war differently. They could push their engines harder during advances. They could maintain pursuit speed without constant concern about temperature gauges creeping into red zones. They could fight longer before mechanical concerns forced tactical retreats. In aggregate, across dozens of tanks and hundreds of engagements, these marginal improvements in reliability translated into operational advantages that defied easy measurement, but commanders recognized instinctively the symbolic weight of Bobby's device extends beyond its immediate mechanical function. It represents something fundamentally American in the conduct of World War II, a pattern that German and Japanese military theorists consistently misjudged. The Axis powers built their military philosophies on concepts of superior technology, tactical brilliance, and warrior spirit. German tanks like the Panther and Tiger were engineering marvels, mounting guns and armor that made them individually superior to any American tank. Japanese naval aviation in 1941 represented the pinnacle of carrier-based air power, yet both nations lost wars they initially dominated, and Bobby's small brass device helps explain why. American military strength in World War II rested not on superior equipment, but on superior systems. The Sherman was never the best tank, but America built 50,000 of them. The M1 Garand was never the most powerful rifle, but it was the first semi-automatic rifle issued to all frontline infantry. American logistics could deliver hot meals to troops fighting in jungles, deserts, and Arctic tundra. American industry could produce landing craft in numbers that made amphibious invasions routine rather than desperate gambles. And crucially, American military culture allowed a mechanic from Indiana to modify critical combat equipment based on nothing more than empirical observation and practical engineering, without formal authorization, without academic credentials, without permission from the experts who knew better. This would have been impossible in the Wehrmacht or the Imperial Japanese Army. German military culture emphasized hierarchy, training, and adherence to doctrine developed by professional staff officers. Innovation happened at research institutes and testing grounds, filtered through multiple levels of bureaucracy before implementation. The idea that a junior enlisted man might meaningfully improve a combat system without explicit orders represented a collapse of discipline, a dangerous democratization of expertise that undermined proper military order. Japanese military culture went further, infusing combat systems with spiritual dimensions where warrior spirit compensated for material disadvantages. To suggest that a mechanical device might matter more than fighting spirit bordered on ideological heresy. Yet here, in a repair depot in England, a barely educated mechanic had identified a critical vulnerability in America's primary armored vehicle and developed a functional solution using scrounged materials and high school physics. No formal research program, no engineering degree, no authorization from the Ordnance Department's technical staff, just observation, experimentation, and implementation. And because American military culture, for all its many flaws and contradictions, maintained space for this kind of informal innovation, Bobby's device spread throughout armored units faster than any official directive could have mandated. The German soldiers who faced the Allied advance in the spring of 1945 expected, based on their experience and training, that American material superiority would come from overwhelming numbers. They were prepared to face 10 Shermans for every Panther, 20 Shermans for every Tiger. They understood that individual American tanks were inferior, but collectively unstoppable. What they did not anticipate, what their intelligence officers could not predict, was that those inferior tanks would become more reliable, more effective, not through factory improvements or design changes, but through the accumulated modifications of thousands of mechanics making thousands of small improvements in hundreds of depots across the European theater. Bobby Hendrix's device was not unique. It was emblematic. Other mechanics developed improved track links that reduced breakage rates. Crew commanders modified gun sights for faster target acquisition. Welders added improvised armor to vulnerable points. Some modifications proved worthless. Some created new problems, but the best solutions spread through informal networks, tested in combat, adopted by crews who measured effectiveness in survival rather than official specifications. The Sherman tank that rolled into Germany in 1945 was not the Sherman that had struggled in North Africa in 1942. Not because of planned upgrades or systematic improvements, but because of 10,000 small innovations accumulated through practical experience. The Japanese military faced similar patterns in the Pacific. American submarines in early 1942 suffered from defective torpedoes, a critical failure that allowed Japanese ships to survive attacks that should have destroyed them. The Navy's Bureau of Ordnance insisted the torpedoes functioned correctly and blamed submarine commanders for poor marksmanship. Submarine commanders who risked their lives with every patrol conducted their own tests, identified multiple design flaws, and developed field modifications that made their weapons effective. They bypassed official channels, violated regulations, and saved the Pacific submarine campaign. When Admiral Charles Lockwood finally acknowledged the problem and authorized fixes, he implemented solutions that submarine crews had already discovered through trial and error. This pattern, centralized production of adequate equipment, decentralized improvement through practical innovation, gave American forces a resilience that rigid military hierarchies could not match. German tanks were superior, but when they broke down, they required factory-level repairs. Japanese aircraft were deadly, but maintenance demands exceeded their logistics capacity. American equipment was designed for field repair, for modification, for operation by mechanically inclined farm boys who grew up fixing tractors. The gap between design specifications and combat performance was expected, accepted, and addressed through a culture that empowered the lowest ranks to identify and solve problems. Bobby's device became official in April 1945, 2 months before the European War ended. An Ordnance Corps investigation, prompted by reports of widespread unauthorized modifications, examined the cooling system and recommended its adoption as a field expedient upgrade for all Sherman variants with radial engines. The recommendation came with technical refinements, improved materials, and proper documentation. By the time official production began, more than 200 Shermans already carried Bobby's original design, installed by mechanics who never waited for authorization that might never come. The recognition came too late to matter much. By April 1945, Germany was collapsing, its armored forces reduced to scattered remnants desperately defending approaches to Berlin. The final weeks of combat saw Shermans rolling through German towns against sporadic resistance, their cooling systems, improved or not, barely tested. Japan would surrender before American armor invaded the home islands. Bobby Hendrix received a commendation for technical innovation, a brief ceremony at division headquarters, and orders to prepare for deployment to the Pacific that never materialized. But the significance of his device extends beyond its immediate tactical impact. It represents a fundamental truth about how democracies wage war, a truth that authoritarian regimes consistently fail to understand. Military effectiveness does not flow solely from superior weapons or brilliant generals or warrior spirit. It emerges from systems that can harness the intelligence and initiative of millions of ordinary people, that can turn observation into innovation, that can implement solutions faster than bureaucracies can evaluate them. The Sherman was never the best tank. It did not need to be. It needed to be good enough, producible in vast numbers, and continuously improvable by the teenagers and young men who operated them. German military theorists, surveying the wreckage of their defeat, struggled to comprehend this. They had possessed superior tanks, superior tactical doctrine, superior crew training. They had fought with skill and determination against overwhelming odds, yet they lost definitively and catastrophically. Post-war analyses focused on material disadvantages, on the industrial might of American factories and Soviet population reserves. These explanations, while factually accurate, missed something crucial: Germany lost not just because America built more tanks, but because those tanks, individually inferior, collectively evolved to meet combat demands through a process of decentralized innovation that German military culture could not replicate. A small brass device, dismissed as useless by experts, installed by unauthorized mechanics, spreading through informal networks. This was not how professional militaries operated. This was chaos in discipline, a violation of proper order. Yet this chaos contained its own logic. A logic rooted in trust that the men fighting the war might understand their needs better than staff officers in rear headquarters. American military culture, with all its contradictions and inefficiencies, created space for a mechanic from Indiana to improve warfighting capability in ways that formal research programs had not imagined. The symbolic object that recurs through this story is not the device itself, but what it represents. The radical idea that expertise exists everywhere, not just at the top of hierarchies, that a 22-year-old with grease under his fingernails might solve problems that defeated engineers with advanced degrees, that the proper response to unauthorized innovation is not punishment, but evaluation, that winning wars requires not just following doctrine, but continually questioning whether doctrine reflects reality. Bobby Hendricks returned to Indiana in October 1945, took over his father's garage, and spent the next 40 years repairing farm equipment and automobiles. He rarely spoke about his wartime service, rarely mentioned his cooling system or the tanks that helped keep running. In interviews conducted late in his life, he deflected credit, insisting he had simply noticed something obvious that others had overlooked, that any competent mechanic would have done the same. This modesty, sincere and reflexive, itself reflects something characteristically American: the simultaneous conviction that individual ingenuity matters and that such ingenuity is commonplace, unremarkable, the expected rather than the exceptional. The M4 Sherman tank, that imperfect vehicle that carried American armor through North Africa, Sicily, France, and Germany, survives in museums and on memorial pedestals across the United States. Visitors read plaques explaining its specifications, its combat record, its role in Allied victory. Few of these displays mention the countless modifications, the unauthorized improvements, the field expedients that transformed factory-standard vehicles into battle-effective machines. The history preserved in museums is clean, official, documented in technical manuals and after-action reports. The history that Bobby Hendricks represents exists in fading memories and scattered maintenance logs, in oral traditions passed between veterans, in the accumulated wisdom of practical experience that rarely survives into formal archives. Yet this unofficial history matters profoundly for understanding how democracies fight and win wars. Authoritarian systems can achieve remarkable efficiency in top-down execution. They can mobilize resources ruthlessly, suppress dissent completely, demand sacrifices unquestioningly, but they struggle with distributed problem-solving, with empowering individuals to identify and address challenges that central planning overlooks. The Wehrmacht's logistical system functioned brilliantly when executing prepared plans. It collapsed when conditions diverged from expectations, because junior officers lacked authority to improvise and soldiers lacked cultural permission to question doctrine. American military culture, messy and often frustrating in its competing authorities and informal networks, possessed a resilience born from trusting people to solve problems. Not always, not consistently. The Army maintained plenty of rigid hierarchies and pointless regulations. But in critical spaces, particularly in combat units where performance mattered more than protocol, there existed room for Bobby Hendricks to install his useless gadget, for crews to adopt modifications that kept them alive, for practical experience to trump official expertise. The transformation this story charts is not mechanical but ideological. German soldiers expected American military strength to come from industrial might, from factories that produced unlimited material. They prepared to fight wars of attrition, where American numbers overcame German quality. This expectation was not wrong, but it was incomplete. American strength came not just from how much equipment could be produced, but from how quickly that equipment could be adapted, improved, and optimized for conditions that designers had not anticipated. The Sherman that landed in Normandy was adequate. The Sherman that crossed the Rhine was battle-tested and field-improved, carrying modifications born from practical experience rather than theoretical engineering. Japanese military philosophy emphasized spiritual factors over material ones. believing that warrior spirit could overcome material disadvantages. This ideology, taken to suicidal extremes, led to tactical decisions that wasted lives and equipment, but it also blinded Japanese commanders to the nature of American military effectiveness. They saw American abundance, the endless streams of supplies, the replacement equipment, the apparent casualness about material consumption, and interpreted it as weakness, as evidence that Americans lacked the spiritual discipline to endure hardship. They failed to recognize that abundance itself was a strategic weapon, that the ability to treat equipment as expendable and replaceable created operational flexibility that no amount of warrior spirit could match. Bobby's device symbolizes American abundance not in its materials, $7 of components, 3 pounds of brass and steel, but in the philosophy it represents. Only a military with absolute confidence in its industrial base could tolerate mechanics modifying critical equipment without authorization. Only a culture certain of its ability to produce more tanks could accept the risk that unauthorized modifications might reduce reliability. The device did not represent material abundance, but the psychological freedom that abundance created. Permission to experiment, to fail, to try unconventional solutions because success mattered more than following procedures. The epilogue to Bobby Hendricks' story plays out in the decades after World War II, as military historians and veterans attempted to understand why the Allies won and the Axis lost. Early explanations focused on material factors: American industrial capacity, Soviet population reserves, British persistence. These explanations satisfied but did not fully illuminate. Later analyses incorporated leadership, morale, intelligence advantages. All true, all incomplete. The full answer requires understanding how democratic military culture, chaotic and inefficient as it often appeared, created systems that could harness collective intelligence in ways that rigid hierarchies could not replicate. Bobby's useless gadget, multiply replicated across thousands of tanks and millions of components, represented democracy in metal form. Not democracy as political philosophy or voting rights, but democracy as applied epistemology, the radical proposition that knowledge and capability exist throughout populations, not just at hierarchical peaks. That a mechanic might understand engines better than engineers, that crews might improve tactics better than staff officers, that winning wars requires not just planning from above but learning from below, incorporating lessons from every level, treating experience as valid knowledge rather than mere anecdote. This democratic approach to warfighting frustrated allies and enemies alike. British military culture, more hierarchical and tradition-bound, often clashed with American informality. Soviet forces, ruthlessly efficient in some ways, remained bewildered by American casualness about doctrine. German commanders, even in defeat, struggled to comprehend how such apparent disorder could produce military effectiveness. The answer lay not in superior American discipline or better American planning, but in systems that tolerated, even encouraged, the kind of initiative that Bobby Hendricks displayed. Not every time, not automatically, but often enough in enough critical spaces to matter. The sound that echoes through this story is not the roar of Sherman engines or the thunder of 75mm guns, but the quiet click of Bobby's device cycling coolant through its chambers, absorbing excess heat, extending engine life by hours and days and weeks. An unremarkable sound, an unnoticed sound, the sound of a system working as intended, preventing failures rather than celebrating triumphs. There are no dramatic moments in prevented overheating, no spectacular successes in engines that do not seize. The heroism of Bobby's device lies in its ordinariness, in the mundane functionality that kept crews alive through unspectacular reliability rather than glorious performance. This is the ultimate symbolism the device carries. Victory through aggregate small improvements rather than decisive breakthroughs. American military success in World War II came from 1,000 Sherman crews fighting adequately, not from a handful of superweapons fighting brilliantly. From 100,000 mechanics making small improvements rather than genius inventors revolutionizing warfare. From the accumulated effect of millions of people doing their jobs competently, creatively, and with just enough latitude to solve problems as they encountered them. The larger truth about freedom and abundance that Bobby Hendricks' story illuminates is this: Democratic societies possess a strategic advantage that cannot be easily quantified or quickly replicated. Not because democratic soldiers fight harder or democratic generals plan better, but because democratic systems can mobilize intelligence across entire populations. They can turn observation into innovation at every level. They can implement improvements faster than centralized bureaucracies can mandate them. This advantage is invisible in the opening stages of conflict, when authoritarian efficiency appears overwhelming. It manifests slowly, incrementally, through 1,000 small adjustments that collectively transform inadequate equipment into effective weapons. The Sherman tank was never good enough. It was only barely adequate, but America built 50,000 of them and then trusted 50,000 crews to make them work anyway. Some crews died in their inadequate tanks. Many crews survived because mechanics like Bobby Hendricks refused to accept that inadequacy was permanent, that equipment limitations were final, that official specifications represented the end of improvement rather than the beginning. This refusal, multiplied across millions of American personnel, converted industrial capacity into military effectiveness in ways that production statistics alone cannot capture. The war ended. The tanks were mothballed or scrapped. Bobby's device passed into footnotes and obscure technical histories. But the principle it represents endures. That freedom is not just a political value or moral imperative, but a practical advantage in any system that requires distributed problem solving. That abundance is not just material wealth, but permission to experiment, to fail, to try again. That victory in complex struggles comes not from perfect planning, but from giving competent people authority to address the problems they alone can see, the challenges that planning from a distance inevitably overlooks. In that cold depot in England, on a gray afternoon in March 1945, Bobby Hendricks held a useless gadget in his blackened hands and prepared to install it in another Sherman tank. Around him, the machinery of war ground forward with inexorable momentum, unstoppable not because it was perfectly designed, but because it incorporated millions of moments like this one. Informal, unauthorized, effective. The sound of hammers on steel, the smell of oil and diesel, the quiet determination of a young mechanic who saw a problem, designed a solution, and trusted that someone would let him try. This is the sound of democracy at war. Not trumpets and anthems, but the patient work of improvement, the relentless accumulation of small advantages, the conviction that adequate equipment in sufficient quantity, continuously improved by competent people, defeats superior equipment wielded by rigid hierarchies. This is how freedom fights. This is why abundance matters. This is the useless gadget that helped win a war.